Happy International Year of Quantum and 50 years of Thai Quantum. My name is Nick Bronn, and I'm calling from IBM Quantum, and I'm here to tell you a few things that we are very excited about to share with the Thai community about what IBM is doing with quantum computing. Behind me is the System 2, which we recently released that has the most performant and modular quantum computer currently available. Let me share some slides with you. At IBM Quantum, we're interested in operating at the cutting edge of scientific discovery with the most performant utility-scale quantum computing technology available. Everyone is freely invited to join us by scanning this QR code, for example, by getting started with the IBM Quantum platform or going to quantum.ibm.com. Let me share with you some of the recent highlights that have taken place since I was last had the opportunity to be in Thailand 5 years ago. First of all, we begun the era of quantum utility. What do I mean by that? Well, we know that certain problems are so complex that the runtime it takes a classical computer grows exponentially with the problem size. And you see that here in this graph, this exponential of classical computation takes off, such that we know there are no problems, there exist problems that no amount of time on a classical computer would ever be able to solve in the lifetime of the universe. The other thing we know is that we have quantum algorithms, for example, algorithms that use quantum phase estimation that allow you a linear scaling in quantum circuit complexity with runtime, which means we know that there theoretically exist problems that we can approach with a quantum error-corrected, fault-tolerant quantum computer, given by this linear line right here in the blue. We're at a very interesting time right now where we don't have quantum error correction quite yet, but more on that later. But rather, we can start to use the quantum computers we have and to use techniques called quantum error mitigation to achieve results beyond the ability of classical computers, yet we are not to the point where we are fully error corrected. What I mean by this is by being very smart about how we run our circuits, we can learn how the noise affects the results and extrapolate useful results from the quantum computer currently today. We call this the age of utility, and we believe we entered it last year with a result that I'm going to share with you. We did a physics simulation called an Ising model, which isn't exactly important for this demonstration, but leave it to say that this simulation took 127 qubits. That is way beyond the scale of the capabilities of brute force classical computation on any supercomputer available today or very likely in the future. Instead, what physicists and chemists do in this kind of case is they make approximate kinds of computations using this mathematical trick called tensor networks, which you may have heard is behind a lot of the advances in AI. They are also very useful for simulating the dynamics of physical systems. We compared our results in the IBM Eagle processor, given by the plus signs, to a number of tensor networks that were both in collaboration with us and independently done by external researchers. See that there's kind of a range, this range in the gray, where the quantum computer agrees with many of the tensor networks, but we actually don't know the correct answer. So any of these answers could be verified by, say, an experiment, or maybe some analytical technique, for example, where we do know the answer, such as the points and the ends at 0 and pi over 2. What this means is we're providing with quantum computers today competitive answers that can only be approximated by the best other classical techniques that have been developed by researchers. We call this the area of utility, and while this is not a useful demonstration, other than to show that we're competitive with tensor networks, we have indicated that we plan on achieving quantum advantage on a useful result by 2026, which is incredibly exciting. Since this demonstration of quantum utility, we have a number of experiments that have been performed both by IBM and external parties without any assistance from us, which have demonstrated large-scale quantum algorithms to provide results that are difficult to simulate with classical computers. And the list keeps growing, and we're very, very excited to see the community take this idea of running these large simulations that are going to pioneer the edge of science. In the future, what we kind of see is in this area of error mitigation was what enabled us to achieve this utility on 127 qubits and was featured on the publication, the cover of the publication Nature. We want to continue running algorithms on noisy quantum systems so that we can figure out what is possible, and we very much do believe that that there's a lot of excitement to be had, while at the same time we are pioneering forms of quantum error correction so that we can suppress the error rates and start to approach some of those fault-tolerant algorithms that would give us proven quantum advantage. And to that case, we even have some great theoretical work, something called quantum low depth parity check codes that allow us to efficiently use quantum resources in performing error correction, and we are moving hardware in that direction. We plan on not just getting to quantum error correction, which I'll talk a little bit more about, but we have been releasing a large amount of software. We have released a stable version of Qiskit called Qiskit 1.0, at this case Qiskit 2.0 to be out soon, which is stable and incredibly performant because we've refactored a lot of the Python internals into programming languages that are more computationally efficient, for example. And we have benchmarked Qiskit against the leading suites of quantum SDKs and found that it is indeed the most performant. At the same time, we are offering more services such as Qiskit functions, which allow a kind of modular usage of our system by third parties. We have Qiskit add-ons that allow modular open source projects with our partners. We even have AI transpiler services, for example, for trying to squeeze the most performance out of the quantum circuits that you build today. But I'm a little bit more excited about the hardware, having had a hardware background. We currently have the Eagle and Heron processors of 127 and 156 qubits, respectively. The Heron has a different kind of 2-qubit gate, which is more performant and has really cut down the amount of crosstalk. So we are seeing large advances in the fidelities of the quantum circuits that we're able to run. As we take the Heron as a base unit, we start to combine the Heron into larger and larger systems in a modular, integrative way, so that we can get more performance out of the system. And then by the time of the end of the decade, we plan on releasing Starling. And Starling is very interested because at this point, we're going to have error correction will be built into the hardware. And so that's extremely exciting. And in particular, we're going to see this jump to the number of quantum gates you're going to run, because the errors are going to be so much lower, you're going to be able to execute extremely long circuits on at least 200 qubits to start with, going up to 2,000 a few years later, which allows that reach of these fault-tolerant algorithms where we have proven quantum advantage. So this is the roadmap that I wanted to share with you, but I just wanted to share one more thing, and that is that we have some, two more things. And that is just to demonstrate that, in fact, we have measured the fidelities of these quantum processors, and we have demonstrated performance as a function of time as we introduce these Heron processors. They are getting much lower errors at the 2-qubit error rate level. Lastly, the algorithm I wanted to share with you is very exciting. We have pioneered this last year in 2024, and we call this sample-based quantum diagonalization. This is an algorithm that uses the combination of quantum processing units and high-performance computing processors to achieve results on a large number of qubits that is pushing the envelope of what can be done with classical computing techniques for chemistry and material science. This particular example was for chemistry, but we have more demonstrated, more chemistry examples. We have a material science example that recently came out, and this was done in conjunction with one of our Heron processors and the Fugaku supercomputer in Tokyo. We can see by demonstrating the algorithm in regimes where we know the exact answers to see how it performs, and then be able to extend this to be very competitive with the best calculations that quantum chemists can perform today. So all in all, the future of the quantum computing industry is very bright. We're very happy to share our successes with you, and we really wish to help you celebrate the International Year of Quantum and 50 years of Thai Quantum. And it's a pleasure to give me this opportunity to address you. Thank you very much.